So today we will continue with strong ETH lower bounds. And we're actually going to show you only 2 reductions today in the entire morning, but they'll be pretty complicated. So the first one, which will be this talk, it's a reduction to longest common subsequence. So we'll show that this simple problem on strings is quadratic hard under strong ETH. And it's like the same proof kind of with other tricks and gadgets, the same kind of proof framework shows the hardness of a lot of like similarity measures on sequences. So sequences or strings are like, just sets of you have n like symbols like letters or points or something. And so you get 2 of them, and you want to know how similar they are. And similarity could be defined in many ways. Some similarity measures are easy to compute, like Hamming distance, for example, between two arrays is like, if they're like aligned. So for every coordinate, you check if they're equal or not. So it's like a linear time problem. But then there are more interesting measures like edit distance, longest common subsequence, a bunch of others, where it's not a linear time computation. You can compute it usually with some dynamic programming, n-squared time. And this kind of proof that I'll show you will show that like many of these, you need quadratic time to compute them. So, okay, so like we'll be having strings of length n over some alphabet, and for the talk, the alphabet will constant size. Like we'll use like maybe 4 letters or 5 letters. The smallest, like binary is like the most. The smallest alphabet you could really work with. And in fact, the proof I will show you can be made to work with binary. It's just much more complicated, so I'm not going to do that. Okay, and yeah, there's a lot of like examples of strings that in the real world that you might be interested in. And I already mentioned in the first day, like DNA is one kind of application of strings. And you may remember this like slide that I showed where this problem of computing some similarity between 2 DNA sequences, it's like people really want to solve it in linear time, and we were wondering, can we do it in subquadratic time or linear time and be correct? And the answer is no. So here's like a list of like similarity measures. So LCS, which we'll see today, is one of them, but there's edit distance, which is like related. Like you want to go from one string to the other with the minimum number of operations. You delete symbol, you add symbol, and you substitute. It's pretty similar to LCS, but a bit different. Local alignment is the one with all these citations. So there, it's a local problem. So LCS at distance, you look at the 2 entire strings, and you want to check their similarity. But local alignment is just finding a substring. Like you want to find the pieces that are most similar. And in the exercise yesterday, you had a problem that was also kind of local. This longest common substring with the wildcards. So there, again, it's like the solution is just a substring. It's very, very local. And you're trying to find like the best substring. And so the reduction in the exercise was probably not that complicated. And in fact, the same kind of proof works for this local alignment problem for biology. And we had that like for a long time. I mean, it was kind of easy to prove. But then it took much longer until we had results for these more global problems. So since that paper, we really wanted to get lower bounds for LCS and edit distance, which are global. And as you will see, it's more complicated. There was a paper of this Fréchet problem. It's a problem on like geometric sequences. So these are like sequences of points, like in the plane or in 3D or something. So you have 2 trajectories. And you want the similarity of the 2 trajectories is defined by saying like if I put a man on one curve and a dog on the other curve, and the man needs to walk the dog, what is the length of the leash, the minimum length of a leash that would work? So for that, there was a very nice reduction showing, again, SETH-Hardness, that you need quadratic time to compute. This was actually a big open question in the geometry community because they were trying to show 3-sum hardness. Like in geometry, you usually show 3-sum hardness. And it was like a big open question with a conjecture that this problem is 3-sum hard for 20 years. And then Carl Brinkman showed that, well, actually, it's SETH-hard. It's not 3-sum hard. But that problem was, again, still kind of a local problem in a sense, or it behaved in a somewhat of a local way. And then there was a breakthrough by Arthur Bakos and Piotr Indyk, where they showed that edit distance, so a global problem, is also SETH-hard. And that result was like people were very excited about it. It was on the news. And then quickly after, we had results showing that even for longest common subsequence, which looks like a simpler problem, even then you need a quadratic time. And there's another version which I'm not even going to discuss. Okay. So the plan for the talk is to show you the hardness for longest common subsequence, because I think it's the cutest out of them. Out of the complicated ones, it's the cutest. So longest common subsequence, right? We have two strings of length n, and we want to find the longest sequence that appears in both. But now it's a subsequence, not a substring, like in the exercise where it has to be continuous. Here you can skip. And yes, you can solve it with dynamic programming in n squared time. And you can also shave some log factors. This is using the 4 Russians technique. How many of you have seen the 4 Russians before? Or know what it is? No? So let me spend 2 minutes on it just so that next time you hear it, you will have heard of it. It's like, you have the dynamic programming table, right? For LCS, right? So it's like you put the first string here. Then you start checking, are they equal or not? If they're equal, you put a 1 and so on. And to fill this entry, you check, like, you take either this, what you had here, like, so you match this and this. And then if the letters are equal, you add a +1. Or you could also take this, which means you match this and this. But then you don't add a 1 because it's like, you're not matching anything. Or this. So this is like what's written there, really, like these 3 options. So you fill this in this kind of order, and it takes quadratic time, because the size of the table is quadratic, and every time you spend constant time. But then what you can do instead is you say, well, I'm going to chop it into blocks of size. So let me show you how you shave a square root log, not a log. No, actually, let's do a log. So you have these blocks of size epsilon log n. So you chop the matrix like this, and now your goal is to fill the blocks like in constant time. So you want to fill this block. You have already know these blocks. So you want to not spend log n time or log squared n time to fill this block. You want to do it in constant time. And the way you do it is it's like you have this huge lookup table where it's like you write, like you say, OK, this block is this block is this block is this. And it tells you immediately like what is the value you should put in this block in constant time. So you create this lookup table. The point is that like because this is just epsilon log n, then the total possible number of strings you can write here is like 2 to the epsilon log n, which is n to the epsilon. So you're going to create a lookup table of size n to the epsilon. And then you do that. But you have to be a bit careful, because like what do you need to say like to know what this value is? Like you need to tell me basically kind of these values, right, and these values, like all the entries here. And you have to tell me these values, like what's written here and here in the strings. Like that's all the information I need to know in order to fill this block. And so this is epsilon log n, and this is again like 2 epsilon log n, so 4 epsilon log n, and to the 4 epsilon. So you choose epsilon small enough, and then you do this. And then the running time is just the number of blocks, which is now n squared over log squared. So that's the 4 Russians technique. It's useful for many other problems. Like the idea is you take, you break your problem into epsilon log n things, you pre-compute the answer Oh, so computing this lookup table, you do this before. It's just like an n to the epsilon size thing. So anyway, and
How do you feel the block in constant times?
yeah, it's you. Actually, you don't feel the block. You just want this really. So you just write this like 2 epsilon log n bits here. So it's like a word kind of. You look a word and you get a word and you use it. So if it's maybe a little bit cheating that you can like access these things in constant time. So okay, maybe log n. So then you shave a log factor. Then whatever. Okay. And this is the best we know so far. Like there's nothing better than this now. Okay, but that's not the point now. The point is like, okay, can we get subquadratic and truly subquadratic into the 2 minus epsilon?
Okay.
Yeah. And we'll show that it refutes SETH. So of course, we'll reduce from OV. Right, so OV, we have 2 sets of vectors, dimension D, just like yesterday. I'm going to color them red and blue. So the A will be red in these slides, and the B will be blue. And we're trying to find, one red, one blue, such that they are orthogonal. And we've seen that getting subquadratic time, we're into the 2 minus epsilon times poly D. So D is log, so this is polylog. You would refute SETH. Okay, and so now we're going to take OV and reduce it to LCS. And the length of the strings we're going to create are like n times poly D, which is near linear, so it's fine. And so I'm going to tell you the plan, and then I'll ask you like how to implement this thing. But the plan is like pretty obvious. You're going to take your vectors, and then you're going to encode them with some gadgets. These are like strings that encode the vectors. We're going to have like the red gadgets, the blue gadgets. They'll be defined a little bit differently. And so they will have like this nice property that, if you look at the LCS of 2 gadgets, then the LCS is large if and only if the vectors were orthogonal. So with the vectors, we want to know if they're orthogonal. Here, we want to know if the LCS is large. So that will be the goal. And then once we have the gadgets, we will just put them together somehow. So we take like the red gadgets, we put them in some long string, and the blue gadgets, and we put them in some long string. Like it's not going to be just concatenation, but it's just. And in terms of parameters, right, the vectors here have length d, and we will have some polynomial blow-up. Maybe it'll be d squared. But we don't care. It's fine. It's just polylog. And then here we will not have much blow-up, so it will just be n times d squared. And then with this like concatenation thing, this final step, it will be very tricky because like what we want is that the LCS of these 2 long strings will really depend on the existence of 2 good gadgets. So the LCS of the long strings should be large if and only if there existed a pair of gadgets that were close. And that it's like there's n gadgets here, n gadgets there, and just the existence of one like pair should affect the global thing. Like so, the local condition should affect the global condition. Okay, so let's create these gadgets, and it'll be like step by step. We'll start with, we were going to start with vector gadgets, but let's even start with coordinate gadgets. So to create these vector gadgets, we're going to look at the coordinates and try to encode them. So how do you prove this lemma? So this lemma says you can create coordinate gadgets, this CG, and there will be 2 kinds, like the red kind and the blue kind. And so there will be like an encoding of 0, an encoding of 1 in each kind. And they will satisfy this property that if you look at 2 bits, you encode them. If they were like the product was 0, so if one of them was 0, the LCS should be large, 2 in this case. And if they are both 1, the product is not 0, then the LCS should be small, like 0. The 0 and the 2 here doesn't matter. The point is that they're different. Like that, in the good case, the LCS is larger than in the bad case. But there's a construction that gives 0 and 2. So I'm going to let you suggest a construction.
So for each symbol, you make 4 symbols. You turn the ones in A into 1, 1, 1, 1, and the ones in B into 4 zeros.
Okay, wait. That's a good start. So this is like the A part, and this is the B part. So in A, I'm gonna encode the 0 and the 1 in some way, and here also. So you're saying the 1 goes to all 0?
So in B, the 1 should go to all 1, so 0 is.
Okay, that already is good because it satisfies the second property. If they're both 1, then there's no LCS. The LCS is 0.
Now you make the 0, 0, 0, 1, 1, and the other way.
Like this?
I think so.
Okay, let's see. So now we have to check that if you take 0 and 0, if you take any of the 3 combinations, 0, 0, 0, 1, 1, 0, and so on, it should be exactly the same, like 2. So with these 2, yes, the LCS is 2. With this, it's 2. This is 2. Yeah, looks good. Yeah, what I have on the slides is essentially the same. Somehow 3 is enough. And notice that like this condition that like it's exactly 2, it's kind of important. It's not enough that it's like, if equal to 2 or equal to 0 or larger. If it was like that, like not precise, then it's going to create trouble for us later in the construction. Because then it's like, suppose that 0, 0 got a score that was like larger than 0, 1. Then when we have the orthogonality, then in one case you have 0, 0, so you get like an extra score, but then other place you have a 1, 1, so it like compensates for it, and then it doesn't really check what we wanted to check. So having precise, we have to work a bit harder for it, but it's very important. Okay, now we move on to the vector gadget. So now we know how to map each kind of bit, and now we have all the entire vector. So we want that to be able to encode a vector, the red vector, the blue vector, in such a way that if the vectors are orthogonal, then the LCS is large. It's like this beta plus 2. And if they are not orthogonal, so there was one place where they are 1, 1, then the LCS is exactly beta. So there's a gap of plus 2. And beta is some function that depends on D. It's some fixed value. Okay, so how do we do that?
You just separate each one with, say, 4 vectors in A, you separate them with 2. 4 vectors in B, you separate them with 3.
2 and 3. What does that do? So you do like the coordinate gadgets, right? And then you're saying you put 2s. And I guess your goal is to say like this will match like this, right? I'm going to pick the LCS of this one, and I'm going to get the contribution of, and the 2s and the 3s are like separators.
Yeah, I think you said you need like matchers, like if you make like big enough matchers, then those have to match.
Yeah. Yeah, so it's like, I think you want to put 2 and 2, not 2 and 3, because like 2 and 3 doesn't really do anything. It's like you could have matched like this, and it's like a mess. The 2 and the 3, but if it was 2 here, and the 2 was like very large, like 2 to the million, then you really want to match the 2, because it's like more important than the gadgets themselves. It's like a million. And then, yeah, you're forced to match correctly. Yeah, so that's a good idea. Right, so you kind of concatenate them, and then you put some separators. And the length of the separators, I'm going to make it like very large, like 3 times d. 3d is like each separator is longer than the entire vector. And it's very aggressive. But then I can be sure that you will not cheat. So you will always pick these together, and then everything will be matched correctly. And then if this is like the right behavior, then what's the LCS? So we are going to get these d minus 1 2s. So it's d minus 1 times 3d. Plus, we get for every pair, we either get a 2 or a 0. If the bits were like the product was 0, we get a 2 plus 2 from the coordinate gadgets. Otherwise, we get a 0. So the contribution is exactly 2 times d minus the inner product. So every time there was a 1, 1, we get a 0, so we subtract. So this is like the LCS. And just to comment, like if I wasn't very aggressive here, if I just put like a 10, do you see what could be an issue? Yeah, exactly. You could have shifted. So it's like you say, well, fine, I'm going to skip this. I don't want this thing. But I really want to match these. And then I match like this. Then I no longer skip. Like I match this here and so on. So I've really only lost one 2 gadget. So I lost 10, fine. But then I gained so much because maybe like if I shift, then I get 2 plus 2 everywhere. Whereas if I went like this, I wouldn't have gotten a plus 2. So it can probably work with this, like if you're more careful, but let's just be aggressive. OK, great. But then are we done? I said it's an attempt. It's not a. So do you see the issue? Exactly, yeah. So it doesn't satisfy exactly which maybe is not clear to you why we need it at this point, but like I would really want equality there. So if the vectors, if they're orthogonal, so in every place it's like one of them is 0, so you get a plus 2 from everyone. Great, you get exactly the beta plus 2. But then if they're not orthogonal, right, there could be one place where they're both 1. There could be 10 places where they're both 1. And then the LCS is not fixed. It's not beta. It's maybe beta minus 10 or maybe beta minus 2 or 20. So that is going to create problems for us later on if it wasn't. So we have to fix it. And this is like this fix is like probably was the most clever thing in the Indic backwards paper. So I'm going to show a very simple fix, but like conceptually it's very important. So do you see how to fix it? So again, what we want is that the score will always be beta, no matter how non-orthogonal they are, no matter how many coordinates they're 1, 1. Okay, great. Yeah, that's I think the cutest solution. Yeah. So why does this? So do you see what happened here? I added a new character, 3, and I put like a lot of 3s here and a lot of 3s there. And then what happens is, well, I have 2 choices. Either I match the 3s, but then I cannot match anything else because it like blocks something from the beginning and the end. So you can either get the beta, or you don't match 3s, and then you match the gadgets, and then it's up to you. Like maybe you get beta plus 2, maybe you get something less, but you can always get beta if you want it. So you get this like threshold. So then the LCS is like the max, either the beta or that thing we had before. And we got the length. Okay, so we're done with the gadget, with the vector gadgets. Now we want to create the long strings. So we want this, this theorem that we can take the vectors and construct these strings. They are long now, or like n times d squared. The alphabet has these symbols. We're going to use one more symbol. And there's some value tau such that if there's an orthogonal vector, a pair, then the LCS is greater than tau. Otherwise, it's less. And here we don't care about equality. Now, this is like the final thing. So we don't, as long as there's a gap, we're happy. So how do you do that? Let me just start with the obvious thing of just concatenating them. Right, so this is like the most natural thing. You just concatenate them. But so what's the problem here?
I mean, if you match the last two, like the last matching.
Exactly. Like the orthogonal pair we're looking for is not like 1, 1 or I or anything. It could be the last one and the first one. That is the one pair that we're looking for. So this is like, okay, if that happened, then like matching them would like prevent us from matching all the other stuff. So like then the LCS we're getting is just like from 2 gadgets, whereas there's this other match where you match everything in an aligned way, and then you get n gadgets. So it's much better for you to go like in line. So like the LCS will not really be affected by the existence of the pair. So how do you fix that?
Maybe add both ends with things that match exactly like this. And then if you get that, then everything else will.
Yeah. So that's kind of the right idea. So you could somehow. So one implementation of this idea is you make one of them longer, like let's say twice as long. So you copy it twice. So you take the n gadgets, and then you put them again. And then what happens is it's like you can, you're free to match like this or in the middle. And the point is like there's one for any pair you want. Like let's say the good pair, you match it no matter where it is. I mean either left or right. And then you can match everything else. So you don't lose gadgets. So, right, but then what is the issue with this?
More force? Like, are we doing enough force to like stop it from splitting?
Right, so splitting is the problem, this thing. So like because there are more gadgets on top than below, then you don't need to match one gadget to one gadget. You can cheat. You can say, okay, this gadget goes, I take some letters from here, some letters from there. And then I get extra score. And yeah, so maybe what you were saying is like I need more 4s because then like when I do that, like the 4 gets lost. But it's fine to lose a 4. I mean, 4 is like going to be very long. Like, think of this as being like d squared 4s. Like, so 4 is very important, but there are like twice as many more 4s in the first string. So I don't care about losing one. So your solution is to add more 4s at the end. Yeah. Good. So then we add more 4s at the end, and hope that this doesn't create more problems. But it turns out that this is enough. So if you do that, then it works. So let's see the proof. Okay. So right, the 4s. So I have gamma 4. So and gamma is like d squared, which is equal to the length. I'm going to choose the length to be equal to the length of a gadget. The length of a gadget was also like this, if you remember from the previous slide. So I'm going to put like exactly as many 4s as a gadget. And then I claim that the theorem is correct with this tau, which equals this thing. So let's see why that is the case. So we have to check two things. First, that if there's an orthogonal pair, if there's some AB that are orthogonal, then the LCS is at least tau. So why is that? Well, it's okay, we want to match the pair, so we match that pair, and then we try to match everything else kind of correctly, as you'd expect. So you match, okay. And when you match that pair, right, you can match all fours in the first string. The reason is that, well, you have enough fours on the sides. So it's like, you go in one direction, all the fours that you're covering are getting matched, but then everything else can be covered with these fours. So you get, first you have the contribution from all fours in the first string, so 2n minus 1 times gamma. And then also, all the gadgets here are getting matched. Not all the A's, but all the B's are getting matched. And then you're getting this beta from each one, and maybe you're getting a +2 from the orthogonal pair. So you get n times beta for sure, and then if there's indeed an orthogonal pair that you're matching, you get a +2. So the score is exactly this. This is from the fours, and this is from the gadgets. Okay, so this is like the first direction. And then now in the second direction, let's assume that they're not orthogonal. So no matter, in this case, whatever pair I match, I will only get beta. I cannot get more than beta. Question? Okay, so in this case, so the contribution from the four, so let's compute the LCS. There's contribution from fours and from other stuff. From fours, it's at most this, because that's like the entire amount of fours, and the first string is this much. So that's an upper bound on the fours. And then what's the contribution from these gadgets? Okay. So let's separate. So there's different kinds of gadgets. Some gadgets could be unmatched completely. That's not a good idea, but it could happen. But then you get 0 from them. Fine. Some gadgets are matched to only one gadget in A, so they don't cheat. But then because we assume that there's no orthogonal pair, then you're only getting beta from those gadgets. And then there are those gadgets that cheat. So you match one gadget to two gadgets. But when you do that, okay, great, maybe you win. You somehow manage to match all of your letters. So you get much more than beta. You get the length of the gadget. Everything gets matched. But then you are also losing a 4. Because if you match to two gadgets, then the 4 that's in the middle gets lost. So then your gain is at most 0. So you better not do that. That's it. That's the proof. Any questions?
Is there interest in like LCS over binary alphabet?
Yes. So for binary, it would also work. It's just more complicated. Basically, the idea is like instead of putting letters, like a new letter to separate stuff, you create like a new kind of string. It's kind of special in a way that if you match it to things that are inside, then it's not, you don't get that much benefit. But yeah, the proof gets more complicated, obviously. But yes, we know that for binary strings, it's hard. Yep. Also edit distance for binary, and yeah.
Do you have any questions?
Next slide. Other questions before I move on?
Will you match two copies of A both?
Sorry?
You only have two copies of everything A, and you will match both copies. Is it a problem?
2 copies, like to the same gadget, or yeah. So yes, matching 2 gadgets in A to the same copy in B, it's a cheating, but it's not the proof shows that it's not worth it.
Sorry, the same vector is you have two
The
gadgets.
same vector has two gadgets, yes,
So you
yes.
the same vector with two vectors.
Oh, so maybe you're saying like A1 and A1, you know, A1 gets matched here, and then A1 gets matched again somewhere else. Actually, it will not happen because you kind of have to be like ordered. So you like, it's like you're matching these to an interval of length n. And so in an interval of length n, there's no repetitions. But even then, I'm not concerned because okay, fine, you match it twice. If there's no orthogonal pair, then the contribution is still beta. So I really care about the you know, if there's an orthogonal pair, I care about it. All the other vectors, I don't care. And in fact, this thing with the trick with the threes on the both sides, this really means that I don't care. Like any gadgets that are not orthogonal, I can really think of. I know exactly what they will do. They will match the threes, and I know exactly what they are giving me. Right. So without that trick, like this would have been a wrong proof, because then you know if you match the orthogonal pair, you are forced to match all what's in the right and what's on the left. You are forced to match it in a specific way. And then maybe you are unlucky, and those to the right, when you match them to the ones on the right there, they're very bad. They're very non-orthogonal. So then you lose so much that it's not worth it. The +2 that you get is not worth it. Okay. Right, so great, we have an answer. These problems are hard, but like, okay, they're using heuristics. What if, you know, if you give me 1.001 approximation, that would be great. Like, what about that? So yeah, so this is a very big open question. Like LCS, added distance, can we get a good approximation subquadratic time? It's open. Like it could be that there is this 1.001 in linear time. We cannot rule it out. So let me say a few words about why that's the case. So, right, so let's look at this reduction. Right, you know, the LCS was this thing which was like n times something. The LCS is like n or n plus 2, n times d, whatever. But it's just a +2 gap. It's like a tiny gap. Multiplicatively, it's like 1 plus 1 over n. So it's like nothing. So I guess you see why it's not an approximation thing. And really, there are two sources here for the issue. And there's like, to fix them, there's like two challenges that are different from each other. So, okay, so first let's talk about the PCP thing. Okay, PCP, this will be the topic of next talk. But in general, like in NP hardness of approximation, like you say, okay, I either have a formula, either it's satisfiable or not satisfiable. If it's satisfiable, then I'm satisfying all the clauses. If it's not satisfiable, then maybe I'm not satisfying one clause. But then the PCP theorem comes and says, no, you can actually assume that if you don't satisfy like half of the clauses or 90% of the clauses. And that leads to all these hardness of approximation results. And but then the hard work is proving the PCP theorem, and that's it. This matters here because if you think about the vectors, if you think about the reduction from yesterday from SAT to orthogonal vectors, what is this orthogonality, like the inner product? It is really representing the number of clauses you don't satisfy. Like if it's the inner product is 0, then you satisfy everything. But then for every clause you do not satisfy, you get a 1, 1. So the inner product is really related to what I just said. So somehow, if you could assume that like SETH, but for approximate SAT, for either it's completely satisfiable or 90% is not satisfiable. Like any assignment will not satisfy half of the thing. Then it would be nice here because then you could say, yeah, like either I get the good LCS, like +2 kind of, or half is I'm getting the inner product being half. So then I get like a multiplicative gap in the vector gadgets. So that would somehow make things better because right now we have like this +2 is like in general, but also in the gadgets themselves. For that, we seem to need like a fine-grained PCP theorem to like PCP theorem has like polynomial blow-up, and so it's not fine-grained. Maybe it can be made like there's a conjecture that you can make a linear PCP, which would prove like ETH lower bound. So it would prove that like ETH is true even for approximate SAT, like something called gap ETH. But here we would need like a super strong, super linear time PCP, which is probably not true in general. But in the next talk, you will see that we can get something that essentially does that. So we have something like that. So that issue is essentially resolved. And it's cool, like it has applications for other problems, not here. But here, for sequence problems, we're still stuck because of the other issue, which is much more serious. So what I said, like what you will see in the next talk, you can really get that the gadgets, they have a multiplicative gap. So the orthogonal pair gives you like LCS 100, and the non-orthogonal gives you LCS 1. So it's like a factor 100 or any factor you want. But we're still very much stuck of the other issue. The issue is like, well, OK, there's one good pair. I'm getting 100 from it. But it's just one pair. There's n other pairs. Oh, the other pairs are not orthogonal. They're not like satisfying assignments. And they will give me 1. So that's a big problem. It's in the language of SAT, it's like what I want to assume is that if a formula is satisfiable, then like there's many satisfying assignments. And if it's not satisfiable, there's no satisfying assignments. Or like in orthogonal vectors, either there's like many orthogonal pairs, like n squared over 10 orthogonal pairs, or n, let's say, n orthogonal pairs, and otherwise there's no orthogonal pairs. But that problem is that this is not a hard problem. You see why it's not a hard problem? Like, I don't need quadratic time. Like, if you promise me that there's tons of orthogonal pairs, well, I can just sample, and I'm going to hit one. I can distinguish with 2 cases. So that's a problem for like this kind of proof strategy. So, yeah, let me know if you have ideas to fix this. OK, so after the break, Nick will tell you about the PCP stuff.